Hi, so I'm Neha, and we're super excited to be interviewing you today. Yeah, so maybe do you want to give an introduction about yourself?
Sure. I am Dr. Marzyeh Ghassemi. I'm a professor at the University of Toronto in computer science and medicine and a faculty member at the Vector Institute. And I will be moving my lab to MIT in summer 2021, where I'll be jointly appointed with IMES and EECS. And generally, my lab focuses on what I call healthy machine learning.
Awesome. Yeah, we're super excited to have you join MIT. I really admire all the work that you're doing, so it's super cool to see that you're joining. Yeah, so about your lab, you do really cool work in healthy machine learning. How do you define that? And
Yes.
can you maybe just tell us a little bit more about the work you're doing?
It's an interesting phrase. I came up with it because I had a good friend of mine at some point tell me, like, you realize, so my research focuses mostly on trying to detect important critical events in healthcare data, right? But all healthcare data comes from human bodies, right? And when do you have data coming off of your body and going into the healthcare system? When you're not healthy, right? And so he made this observation. He said, we actually have no idea what it means to be healthy because we have no data on anybody when they're healthy, really, by and large. And in fact, when you go into the hospital, the more ill you are, the sicker you are, the more data we get on you, right? Because when you're maybe just a little sick, maybe I'll take a one-time blood pressure and get an x-ray. But if you're really, really, quite acutely sick, then suddenly it's constant monitoring. I have your blood pressure, right? I have all this stuff continuously. And so we have sort of this sparsity of data on healthy people. We really only know how the sickest of the sick sort of behave in these critical care environments. And so it's not like normal machine learning where we show images of cats to models and then we say, cats are a thing that you would see in real life. I'm going to show you many pictures of cats in different angles, and I want you to be able to recognize a cat when you're in a self-driving car going down the street. It's now the situation that we're doing outlier detection, like, will this person need invasive ventilation in an outlier data set, really unhealthy people who made it all the way from triage into the hospital, past general internal medicine, into the intensive care unit. And so it's this really strange sort of high dimensional outlier detection in outlier data. And so I call this healthy machine learning because when you're working in health, you want to make sure that the models that you train are working well. And that's really hard to do. Often they become ill-conditioned or maybe buggy, right? Like they don't behave in ways that we expect them to, in the ways that we've seen really good high capacity machine learning models work in other domains, like in imaging or in natural language processing, because this data is so strange because we don't have a lot of healthy data.
That's such an interesting take on it, and it's so important and it's so true. But yeah, that's just very very true. I've never thought about it that way. That yeah, we're missing a lot of
Yeah.
data that normally would be sort of like ground truth for what we're supposed to be like. That's
Yeah.
so
Yeah.
true.
Yeah.
Yeah, you mentioned that healthcare data is really high dimensional. I guess like what do you think is like the difference then that makes it harder to process alongside like we don't have, like as you said, healthy data, but what makes it harder to process than, let's say, like the cat dogs of the ML
Right.
world?
I think there are three things that sort of characterize it right now, at least. So one, it's very heterogeneous. It's not just imaging data. It's not just text data. It's not just tabular data. It's all of those things, right? So like if I really want to know how well your primary care doctor thinks you're doing, I need to read through the notes. If I really want to know how well a fracture is healing, I need to look at X-ray images. If I really want to know how well your diabetes is being managed, I need to look through your lab data, which is tabular data, right? And so all this data is just really heterogeneous. And so it's not like you can say, we developed something that works well on text data. We developed something that works well on imaging. It has to use all of the data, right? To get a more accurate picture holistically of what's happening. But even when we think about like heterogeneous data, if we had a way to ingest all of that and model it, there's still really strange sparsity in health data, right? Because often data is not recorded because maybe a device falls off of you when you're in the intensive care unit and things are crazy. And so, I look over, I'll replace that later. Or maybe they're recorded, like I take a lab test, but if it's not in a bad range, if it's still in a healthy range, I don't put in the exact value. I just put in, below some threshold, right? And so I don't have this raw data. I have sort of, this processed version of somebody's subjective understanding of whether, what this value should have been. Or finally, you could record it and it could make it to the healthcare provider. So maybe I know that you need a specific medication and I know that I sent that medication to the pharmacy, but I have no idea if you picked it up, right? Or even if somehow I was able to get the pharmacy records and then like integrate that in, I would still have no idea if you were taking it on a daily basis, right? And so there's all of this sparsity in this heterogeneous data that makes it really hard to work with. And then finally, there's just a complete lack of ground truth gold labels for many conditions. And so we don't know what a healthy pregnancy looks like, even though half of the population of the world has, gone through, or maybe someday will go through this condition, right? Like it has not been well studied or well established what healthy pregnancies can look like. There are many conditions like endometriosis, just so many conditions that have not been well studied and well characterized. And so if you ask me, how well is this person doing? Often I don't have an answer because there is no gold standard answer about whether we're at different levels. And often clinical knowledge changes, right? Like over the years, people change definitions of what is autism? What does it mean to be on the spectrum? What are various mental health conditions and how are you diagnosed with them, right? What is a healthy weight? What is an unhealthy blood pressure level? Is good cholesterol good, right? So all of these things change over time. And so if you're making a model, it's really nice to say a cat is a cat is a cat. And we know that object detection is important because humans do it and we all recognize objects. And so we can all agree that you should detect objects and we can all agree that a cat is different from a dog, right? Like those are things that you could, go to Amazon's Mechanical Turk, recruit 1,000 people and they would all label things consistently. But you get medical experts who have been trained for decades, right? Often, and they can look at exactly the same data and they are allowed to disagree and say, well, I think it's this. No, I think it's this, right? And so we're really just, a lot of what we do is in more discovery mode, trying to find consistencies or trying to find inconsistencies in the data that we observe.
Yeah, that makes a lot of sense. And yeah, that's so true because, when you're working with and we talk a lot about like data processing and I'm sure that's very important, but like it's so much harder to do when you're not sure what even it's supposed to look like. Because on the other hand, you could be like, okay, I want these handwritten digits to look more like recognizable written digits, but that's so much harder when it's like a brainwave or something. That makes a lot of sense. So you talked about like working with medical experts, which definitely seems to be one of the major themes of the domain. And so we talk a lot in ML about like kind of who the decision maker is and when to defer to the domain expert. So in your case, when do you think is the right, or like not really the right time, because I'm sure it depends, but like what does that look like when you're thinking of, oh, how do we learn to defer to the expert, and at what points should it be the medical professional and at what points should it be the model?
I think you always want to defer. Like the final decision, I think, should always be a deferral. I think that the real advantage of machine learning, like the real benefit of machine learning, is that it could automate these really tedious tasks that honestly machines are better at than humans, right? We no longer train children to do huge columns of numerical sums. That's not like the primary purpose of getting kids out of school because we have calculators now, right? And so we're able to say, as long as you know you could do it if you had to, now use a calculator to do that, let's move on to algebra, right? So I think that that's kind of the goal, right? Like you would hopefully be able to automate things that humans aren't very good at doing ad nauseum. It's not really our forte, and allow the clinicians to actually provide the care for the patient, feel like they're providing compassion, feel like they're considering the patient's wishes and their individual situation in the care decision. The other possibility is that, maybe it's not just tedious tasks here. Maybe we could actually augment clinicians and give them superpowers, right? We could identify features of x-rays that they weren't aware of, things that were unknown previously to be strong predictors or indicators for specific conditions. And, this is not that different than saying we really need MRI machines, right? In order to give us this extra set of information that I can't go do by myself. Really, I need this extra set of information that can be obtained by another system, and then I will factor that into my decision making.
Yeah, that makes a lot of sense. And it's good to hear that it's always deferring, because I think with a lot of people, when they hear about health ML, they become scared to think like, oh, an algorithm is now suddenly going to be dictating my own medical decisions. But that's really like not the case. It's like enhancing what doctors can do. And that's such a different way to look at it. And I think it makes everything like, I don't know, maybe in a more positive light, where people feel comforted that they're getting the best care possible.
Yeah.
So taking a slight pivot, you've also done really incredible and important work looking at biases in clinical settings, from chest x-rays to clinical-based word embeddings. So could you talk a little bit about your work there, and how do you think bias in the field can be handled in sort of a preventative way rather than after the fact? Like we do a lot of work like looking at bias after it's already been embedded in the machines, and we're like, this is such a problem, but how can we do this sort of beforehand so it becomes less of a problem while we're building the machines?
I think that that's a really hard question. So in terms of characterizing the work I've done, a lot of this work was triggered by conversations I had at the end of my PhD 3 years ago, where I had a clinical collaborator say, you've trained all these really interesting models that predict all these really cool things. That's really great. How do they do on minority patients? And I said, well, I feed in this data from, minority patients, and I also feed in their ethnicity. And so I'm sure it's fine. And he said, maybe you should go check. And so I did, right? And, lo and behold, right, it's not fine. Which maybe I think is in retrospect, a lot of these things are very obvious. But when you are training a model, I think it's hard to understand or fully appreciate how pernicious these biases are. And so I want to differentiate between, maybe two things. So the first are biases that might be explained by lack of data or lack of representation, right? So we just don't have enough data, right? So maybe you could say in the models that I train in the Boston area, like those machine learning models, maybe you could say, well, there are not that many African-American patients in these data sets because there aren't that many African-Americans in the Boston area. And so if I have a gap in performance, some of that could be due to a lack of data, and maybe you could address that in some way, right? But then there are other really, the one that always really gets me is that these models underperform on women. I'm like, we're the majority, like you can't, it's not explain awayable, right? And so I think that there's a much harder conversation about how bias in a system gets embedded into machine learning models. And I think it's worth considering the pipeline, right? And so we wrote a review recently, myself and a bunch of co-authors, on ethical machine learning in health, and how this is really a pipeline problem. It starts with problem selection. What do we even choose to study? Nobody studies endometriosis except one new researcher, which is great, Columbia, Noemi. Very few people study, conditions that belong to either minoritized, stigmatized, or historically underrepresented groups in these fields, right? Because they just they don't think of it, right? Or they don't think it's interesting, or those proposals go in and then they're not funded. Once you have, your problem selected, there's also the question of data collection. There's a lot of bias in who can participate in these kinds of studies. So I'm running a study on healthy pregnant women right now with one of my colleagues. And one of the things that, we're having trouble with is we talked to the staff, the clinical staff, and said, we need these 5, measures, these 5 variables. And they said, if you add this 5th variable on, it's going to add another 10 minutes to their appointment time. You will only get wealthy patients, because our patients who are not wealthy squeeze these wellness check-ins in between back-to-back their jobs, right? Often multiple jobs that they are working. And they're trying to get as much work done before they have the baby, and they are forced to go on sometimes unpaid maternity leave. And so if you say that, variable 5 has to be collected, you're only going to get wealthy patients because nobody else can afford 10 minutes. Like, we can barely get them in here for their wellness checkups as is. It's that kind of awareness that I think it's such a small detail that I would not have been aware of in the scheduling of the meetings and how much physical time, like clock time, each variable is going to take. And then we go through in the paper, like, let's assume you do have good data collection, right? What about how you define outcomes, right? Outcomes often are very different for different subpopulations, right? Like, what does healthy look like? What does a good recovery look like? Often that's based on our understanding of what those things are in a small, wealthy subpopulation. Or even within algorithm development, we often impute things to a mean. Who do you think is represented best in the mean, right? It's like the body of this distribution right here, right? We ignore the tails, right? That's a really fundamental concept in most of the algorithms that I teach in machine learning. The tails are outliers. Learn the body of the distribution, chop off the tails, right? Well, who do you think lives in the tails? Minorities live in the tails. And so if you are using models that are saying, really just focus on like the body of the distribution, forget those tails, those people live in those thresholds, right? And so you have to understand who is going to be marginalized when you make those choices. And then finally, going back to our conversation about who makes the final call, let's assume we do everything right. Like, we picked the right problem, we collected the right data, we defined the outcome well, and we developed the algorithm perfectly. That doesn't mean it's going to be deployed in a way that is equitable or in a way that actually advances equity on the ground, right? Like, it just, who's going to be able to implement this model? Wealthy hospitals. What patients are going to benefit from this care? Wealthy patients, right? So I think that there's no simple fix to any of these things. These are just things that you need to think through as you go through and do research, right? That we have to continue to improve as much as possible. And I will say, I actually think machine learning is a really great forcing function for this, because if you look at the clinical epidemiological sort of literature, right, it's not like doctors aren't biased, right? Especially if you've been following the fantastic set of articles in the New York Times, we know that Black women die disproportionately more in childbirth, and it's not because of their income, and it's not because of where they live, and it's not because of their health conditions. It's because of social bias, because all of those hypotheses have been tested and proved false. And so we know that social bias leads to poorer health outcomes for some people, okay? And so, knowing that these things exist and have existed for so long, again, like, doctors are humans, humans are biased, doctors are biased, right? Now we're starting to talk about, well, I don't want a killing machine, I don't want a killing algorithm. Okay, let's institute checks. And maybe everybody could be checked now. I, for one, would feel much more comfortable if there were some sort of way that you could report on or audit medical performance across some guidelines, right? You hear sort of stories come out about how hospitals will have a specific doctor that performs really poorly on one kind of patient, but they don't want to fire this person for the liability risk, right? They might countersue them, and then every patient who has come into the hospital of that minority class who had a poor outcome might say, well, maybe my poor outcome is because this doctor was biased, right? And so it just opens up this huge set of legal considerations. And so often they just sort of encourage them to leave and they go somewhere else and redo the same thing. And so I think having really strong guidelines by regulatory bodies about what kinds of subgroups we need to expect equal performance in would be great for machine learning algorithms, but maybe we could also do that in non-machine learning settings, right? So for hospitals where humans are practicing.
Yeah, wow, no, definitely. That makes so much sense. And especially what you brought up about Black maternal deaths, that has been something that we've been seeing for so many years now, almost, and it still doesn't have a fix. So it's so true that it's not just in machine learning, and it would be very, very wonderful if ML could be the driver for that. And I think we've been able to especially see that exacerbated during COVID, right? Like all the fault lines that already exist in the medical setting have just become worse.
It's small things too. Like I didn't realize that a lot of the pulse oxygenation measures, they don't work on Black skin. And I was like, who approved that? Like that's what?
Yeah. Yeah, no, that's crazy. And so, yeah, no, you're totally right that it's something that has to be done at every level of the system for it to come to the final outcome. So we are running out of time. So we do want to ask you our sort of final wrap-up question, which we ask all our interviewers, and that's, how did you get into machine learning? And do you have any advice for younger students who also want to enter the field?
I got into machine learning through a very long sort of roundabout, windy path. You have to understand machine learning is an amalgamation of 5 different fields, right? There's a little optimization, there's some data science, there's some statistics, there's some neural networks, there's some there's many, many different fields that sort of came together, and now we kind of call ourselves machine learning, right? And it's very broad. It's really an amalgamation field. So I got into it during my master's. So I was at Oxford, and the professor who I was working with, Lionel Tarasenko, said, you could work on this project, or you could work on this, sort of harder machine learning project, and you don't have any experience in that. It's with a bunch of vital sign signals, and you'd have to try to predict acute hypertensive episodes in the ICU where your blood pressure drops suddenly, right? And so this can happen for people who have orthostatic hypotension when you stand up, but for other people, they just have trouble maintaining their blood pressure. And I thought, oh, I really want to do that. That just sounds like an interesting problem, right? And then from there, when I was done with my master's, he said, you really, I think, would enjoy being a student at MIT under one of these faculty members. And he named specific people. And so I applied and I got in. And it was really there that I continued to just dig into the field and find my space. I think that the thing that I would say to people who want to get into machine learning is you should. It's the fun thing about machine learning is that it's very creative, right? A lot of the research work in machine learning is incredibly creative. It's about, how do I take an ill-defined problem and pose it as a problem that can be solved with all of these tools, these algorithmic tools that have come together for machine learning. That gives me a baseline solution. That's not working really well. It's also killing all the Black women. Now, how do I improve this algorithm so that it can do better in these cases that I think are really, really interesting, right? And, you can shoot off and do the theory behind how you diversify subsamples. You can decide, no, I really want to think about robustness and how this might characterize in other settings where there are minority ethnicities that are not African-American in other countries. You can think about, how does this extend across different data types? It's just a very creative field. It's very open, right? I also think that machine learning has had a very strong reckoning with the anti-minority, anti-female culture that has been really strangely dominant in many fields of computer science. But machine learning specifically, like the leaders in our field have tried to address this head on. And I have seen some of the best and most inspiring messages of, I don't care if you, look different, or if you are from a different background, your ideas are great. Participate with us. And not only I don't care, but I know that having a more diverse team means I'll have somebody on my team who says, oh, did you ever think about view X? Right? Where I didn't think about that. And that's an important thing that I do want to think about. So I think that it's an exciting time to be in machine learning. I would say, because it's so broad, there's so many subparts of it you could be in, on the more, software development side, on the algorithm development side, on the theory and proof side, on the data science side, on the audit side. There's so many things you could do. So I'd encourage people to check it out.
Well, that's a wonderful note to end on. Thank you so much for your time. This was a great interview, and we're so excited to have you at MIT. It sounds like the work you're doing is incredible, and yeah, we're just excited to see you here.
Thanks for interviewing me.